So, the long-promised bonus lecture on the metabolism of alcohol. This is considered here exclusively as a case study for an important biological redox process and from the perspective of energy metabolism. It doesn't consider any other physiological, psychological or social issues which may arise from alcohol consumption. Moving on. So that's what we're going to have a look at. Say a link back to what we've talked about in the previous lectures about redox processes. Talk about where it happens and explain what the heck the skewed redox state of the liver is, which is a great phrase. Okay, so alcohol is a drug as defined in a moment, but first, this is all tosh, utter tosh. So-called detox diets have no scientific basis for the claims they make. The liver is our main detoxification organ and has been doing such a job for probably billions of years in our evolutionary history. Similar processes found in fishes, for example, who diverged from us a long time ago. But detoxification is rubbish. Some definitions. Drugs are exogenous substances that affect physiology and psychology. So exogenous means originating or produced outside of the organism. Also refers to substances present in high concentration and normally found in the body. That's a bit rarer. Endogenous, conversely, means originating or produced by an organism as part of its normal biochemistry. And exogens are sometimes, xenobiotics and exogens are sometimes sort of alternate phrases for the same thing. Typically, when we ingest exogens, our biochemistry tries to get rid of them, which is what the liver does, usually by excretion in the urine. This is detoxification. Most of its chemistry, as I said, takes place in the liver and is often involved in increasing the polarity of molecules. So polarity, as you may recall for biochemistry, is charge distribution in the molecule. The more polar a molecule is, the more water soluble it is. The reactions that do this here involve redox processes and are also linked to energy metabolism, of which more later. So the alcohol oxidation reactions take place in the smooth endoplasmic reticulum of mitochondria. These will be covered in the cell biology lectures. And if you read in the notes here, there's some definitions of the various technical terms that are used in this image. As mentioned earlier, our biochemistry tries to get rid of exogens like alcohol by making the original molecule more polar, so more water soluble. It does this by two types of reactions. The second class, conjunctions, are involved in the metabolism of molecules like paracetamol. For alcohol, the chemical processes involve changing functional groups, broadly speaking, so essentially they are type 1. We don't need to worry about this anymore from this point. So alcohol metabolism. This is the most significant difference between alcohol and other drugs. Large quantities are consumed, gram quantities often, whereas in pharmaceutical drugs, milligrams and often micrograms are consumed, so a very big difference in quantity here. And this has quite significant effects on the influence it has on our metabolism in general. So some general considerations, you have a read through them. I guess the main ones are that the consumed alcohol rapidly spreads across tissues and cannot be stored. Like other molecules, we get energy from like lipids, carbohydrates or even proteins. Most alcohol is metabolized in the liver, which is why this organ is subject to damage in the case of extended or excessive consumption. These are the three main routes, in which the ADH, the alcohol dehydrogenase route, is the most important. We all have the other two, but chronic drinkers tend to have enhanced use of the MEOS and catalase routes. These aren't discussed here, but if you're interested, you can find in most, if not all, biochemistry textbooks. We notice that overall, all three routes convert ethanol, that is to say alcohol, first to acetaldehyde and then to acetate, which is effectively acetic acid, though we normally think of it in biochemistry as just the acetate ion. So acetic acid, which of course is vinegar, an important molecule in energy metabolism. So as I mentioned, ADH is the most important route. It seems to have evolved for a number of reasons. It deals with alcohol produced by the anaerobic bacterial fermentation in the gut. So a large number of bacteria in our gut produce alcohol. This alcohol goes straight to the liver via the portal vein and has little physiological effect. It's not produced in large amounts, but it is produced more or less continuously. And the ADH enzyme is also involved in the oxidation of many alcohols, steroids and fatty acids. The difference here, as I mentioned a couple of slides back, is oral consumption of significantly large amounts. So this is the basic process. Ethanol gets converted to acetaldehyde, which then gets converted to acetate. And above the line for these, we have the enzymes involved. ADH, alcohol dehydrogenase, and ALDH, aldehyde dehydrogenase. The dehydrogenase is a clue to their function. And we can see associated with this, at each step of the reaction, a molecule of NAD is reduced to NADH. So in effect, what happens is that a hydrogen is removed from this molecule and gets added to NAD to make NADH. Pause the video presentation, think about the other side of the redox process and how this is a redox process overall. So if you pause the video for a couple of minutes and have a think about this. Okay, let's assume we've done that, so we'll have a look at the summary. If you look at the C1 of carbon of ethanol, it's oxidized to acetaldehyde. That carbon has lost a hydrogen and gained an oxygen. Similarly, the carbon in that acetaldehyde loses a hydrogen and gains an OH when it's converted to acetate. In both cases, these are oxidations, while at the same time NAD is reduced to NADH. So it's a redox process. So the story so far: each molecule of ethanol uses up 2 molecules of NAD in its conversion to acetate, which it turns out is quite a lot of NAD. Okay, so this is a quick sum, back of the envelope stuff, but basically true. Vodka has an ABV, that's alcohol by volume, about 40%. So the ethanol in it has a density of 0.78 grams per mil with a molar mass of 46. So if you do the sums, and it's just a simple proportion sum, a 50 ml measure of vodka would contain 20 mils of ethanol, which weighs 15.6 grams of ethanol. So that's a reasonable amount. So 15.6 grams of ethanol in a 50 ml shot. Work it out as moles. Using that formula there, which you're probably familiar with from biochemistry, comes out at about 0.34 of a mole of ethanol per 50 ml shot. Now this is NAD again. NAD's got a molar mass of 663, and as we discussed earlier on, since each molecule of ethanol uses up 2 molecules of NAD, we can calculate that a 50 ml shot of vodka uses around 450 grams of NAD, which needs to be reoxidized to NADH sooner or later. Otherwise, other biochemical processes involving oxidation reduction cannot take place. Hence the phrase, the skewed redox state of the liver. It's skewed towards NAD being in the reduced form, rather than the normal form where you'd have a balance between the oxidized form NAD and the reduced form NADH. So in principle, this is a substantial fraction of the mass of a human liver. It's even more of an issue for women whose livers are smaller both in absolute and relative to body size terms. As I mentioned earlier on, it's a bit of a back of the envelope calculation, but broadly speaking it's correct. So this is a slide from the A Pill for Nutrition lecture. As discussed before, fat has the highest energy because, being hydrophobic, it is essentially anhydrous. Proteins and carbohydrates are always associated with large amounts of water and often bound by hydrogen bonding. Ethanol is infinitely soluble in water, though people don't drink absolute ethanol, which that would be a terribly bad idea. Now the point about this is it's a lot, as we've discussed, and we have no biochemical mechanism for controlling the metabolism of alcohol. When it is in our system, it is preferentially used for energy metabolism and generation. So we do not use other recently consumed or stored lipids or carbohydrates, for example. And this may have long-term physiological consequences, as described in the slide there. ethanol takes over our energy metabolism while it's in our bodies, and it takes a while to get out of our bodies. It takes probably about 24 hours. Okay, so last word. This should be last word 1, I think. Sorry, last word 2, yeah. Methanol. The metabolism of methanol follows a very similar reaction path. Methanol is found in counterfeit alcohols, such as that one shown. There are some links. I haven't put many links in this lecture, but there are links here too. Some links on counterfeit alcohol. When metabolized, this counterfeit alcohol containing methanol produces a highly toxic formaldehyde and also formic acid by the same mechanism we saw earlier on. Consumption of methanol can lead to serious issues, including blindness and even death, due to these toxic metabolic processes. So on that cheerful note, that's all, folks.